In this segment, we'll be talking about solving quadratic equations. Quadratic equations have a quadratic polynomial involved in them, and actually quadratic equations are all the equations that can be placed into this form, where we have that quadratic polynomial on one side of the equation and 0 on the other side. We're going to look at 4 methods of solving quadratics: factoring, extracting square roots, completing the square, and the quadratic formula. The method of factoring involves the zero factor property. That is, if these two factors are multiplied to give 0, then it must be the case that either A is equal to 0 or B is equal to 0. And we use the idea like this in solving quadratics. You take the quadratic equation, you factor the polynomial. Now we have the product of two factors set equal to 0. So it must be the case, for this to be true, that either this factor is 0 or that factor is 0. And all we're doing in finding a solution, is finding the value of the variable that causes the statement of equality to be true. So if we can find a value of x that will cause this factor to be 0 or this factor to be 0, then we have solutions to the equation. Well, let's see. By observation, we can tell that when x is 6, this factor becomes 0. So x equals 6 is a solution to the equation. Also, this factor becomes 6 when x equals -2. So here are the two solutions to the equation. We could verify them as solutions by popping these values of x into the original equation. Now, by the way, I just identified the values of x by observation that would make each of the factors equal to 0. If the factors themselves become a little more complicated, like there could be a coefficient other than 1 here on x. And in circumstances like that, it's not easy always to just visually identify the solution. What you can do is this. You can set up a little linear equation by thinking, gee, I'd like to know the value of x that will cause this expression in here to be equal to 0. So I'd like to know what will cause x plus 2 to be equal to 0. And solving this, we find x to be -2. And if it's more complicated, then this, though, will take care of that complication. Here's one where we have a factored form on the left side of the equation, but it doesn't mean that we set these factors equal to 0 or we identify the value of x that will cause them to be 0. Remember, the form that we want is a factored form on one side and 0 on the other side. So what we really have to do here is expand on the left and take this -10 and get it off of the right side of the equation. So we would proceed like this. I'm multiplying here, so we have x squared. The middle term, -7x plus 4x, that's -3x. And then -7 plus 4 is -28. And now I'd like to get rid of that -10, so I'll add 10 on both sides. Now, in the interest of time, and because it's so easy to do so, adding 10 here gives me -18. I'm going to just do that in one step. Now I can go to the factored form here, and I'll have the form that I'm looking for solution. I've got x times x for x squared, factors of 18. Now the sign here is negative, so we have the plus-minus combination. And I want those factors of 18 to be collected to give 3. And so the 6-3 combination is what works. I have the 6 here and the 3 here. The values of x that will cause each of the factors to become 0 are solutions. So one solution is x equals -3. The other is x equals 6. Here's a situation where we have x squared equals 25. And if we were solving this by factoring, we would put both terms on one side and factor. And the solution would look like this. Subtract 25 on both sides, factor over here, set each factor equal to 0, or ask yourself what value of x will cause each factor to become 0. We find that x is -5 or x is 5 for solutions. But there's another way to think about the problem. Now, notice here, the structure here is this, that we have a variable squared set equal to some real number. Now, in that situation, you can kind of ask yourself, gee, can I identify a value which, when squared, gives me 25? What number squared gives 25? What number used as a factor twice gives 25? Well, all of those are requests for square root. They all mean square root. You see, and we've had that kind of thing before. So if we have x squared is 25, x then is the square root of 25. Actually, it's plus or minus. It's either the principal square root or the other square root of 25. So x then is plus or minus 5. Right, our two solutions. Now notice how fast we arrived at solutions here versus up here. This is the method of extracting square roots. So it's the idea that if we have a variable squared on one side and a real number on the other side, we can apply this idea of extracting square roots. Now here we have the variable squared, but it has a coefficient attached to it. And one way to handle this is to divide by 4 on both sides. So we would have x squared then is 9/4. And now apply the method of extracting square roots. X then is plus or minus the square root of 9/4, or x is plus or minus 3/2. Now here's one where the variable is a binomial. That is, it's a variable quantity. So we have a variable quantity squared set equal to a real number. So we can say then that that variable quantity, you see, is equal to plus or minus the square root of the real number. That's the idea. And now we have, let's see, x equals -5 plus or minus the square root of 20. Now let's see, 20 is 4 times 5, so this is 2 the square root of 5. So these then are our two solutions. Now I say two solutions because one solution is -5 plus 2 root 5. The other solution is -5 minus 2 root 5. In this problem we have the variable quantity squared, then -9, both on the same side of the equation. To set ourselves up for extracting square roots, we would place the variable quantity squared on one side and then the 9 on the other side. We do that by adding 9 on both sides here. So adding 9 on both sides gives us x minus 2 squared equals 9. By extracting square roots, we know that x minus 2 is plus or minus the square root of 9. We know that plus or minus the square root of 9 means plus or minus 3. So x then is 2 plus or minus 3. And now we can identify our two distinct solutions. 2 plus 3 would be 5. And the other solution, 2 minus 3, would be -1. Take a look at this pattern. We know that if x minus 2 squared is 5, that by extracting square roots, x minus 2 is plus or minus the square root of 5. So x is 2 plus or minus the square root of 5, our two solutions. Oh, by the way, you notice that the solutions here are irrational, and in the previous problem they were rational, so we can get both kinds of solutions using this method. At any rate, now let's go back to the original problem. I've just repeated the problem here. Now I've expanded the left side. I've just squared the binomial and I get this. I subtract 5 on both sides and I get this. Now notice that from this form, if I were solving this quadratic equation, I would have difficulty factoring, and so I can't solve by factoring, and yet the equation we know is solvable using this idea of extracting square roots. Is there some way then that we can go from this form to this form? Well, there is a way to do that, and that method is called completing the square. That is, we can take the original equation and we can rewrite it. We're going to rewrite this as a quantity squared, as a binomial squared, you see. And that process is called completing the square. Okay, here's how it goes. We're going to first of all take the existing constant term and kick it out. We're going to add 1 on both sides. That gives us x squared minus 4x equals 1. Now notice I'm leaving some space here. The space is left for a new constant term that I'm going to invent. Now you invent the new constant term like this. You say you take half of this rascal and then square it. So half of 4, 2 squared is 4. I'm adding 4. Now whether you think of this as taking half of -4 or half of 4, it doesn't make any difference because when you square it's going to be positive anyway. So we have this. Now adding 4 on here, on this side, however, means that we need to add 4 over here to maintain the balance in the equation. All right, and now we factor over here, and this turns out to factor as, I'll go through the long method. We can take a shortcut on this in the future, but using the long method of factoring, I have x times x for x squared. The last sign is positive, so these two signs are the same. They're both negative because of that. factors of 4, 2, and 2. Notice that it is x minus 2 squared that we have here, and 5 on the other side. And now we can use our method of extracting square roots. Now this idea of completing the square, what we're doing really is we are completing a trinomial square. You see, this trinomial is a square because it factors into a binomial squared. A binomial squared, and when it is squared, we get a trinomial square. All right, so we are completing the trinomial square. That's the idea. Let's go through it again. We have this quadratic equation to solve. And let's say we can't factor it. We can't factor it using the methods that we know about right now. So we would go about solving by completing the square. And to do that, we take the existing constant term and kick it out. Now that means we're taking the 2 and subtracting 2 on both sides. So we have, let's see, x squared minus 6x, leave a space, and minus 2 on the right. And now we complete the square by taking half of this and squaring it and putting the result right here. Half of 6, 3. 3 squared is 9. I'm adding 9 here, but if I add 9 on the left, I have to add 9 on the right in order to maintain the balance in the equation. Factoring here, this becomes x minus 3 squared. Negative 2 with 9 is 7, and away we go. Now, let me show you how I factored this so quickly. It turns out that when you take half of that amount and then square it, that if you really write this as, if I wrote this amount as like that, I'm actually distinctly identifying the amount that I'm squaring to give that term, then this will become that. Sometimes it's handy to do that, to just leave it in sort of a raw form in order to go to the factored form. It's not really important in this problem because all the numbers are pretty simple. But if this were a rather complicated situation, like a fraction, for example, or some big numbers, incredibly big numbers or something like that, then I would want to identify specifically the amount that's being squared. That is, I'm identifying specifically half of this, and I put it in parentheses, and I show that I'm squaring it. Now, I perform that squaring to put the number over here, but by leaving it in this form, I'm identifying the second part of the factored form. Okay, with that in mind then, I have a condition where I can use extracting square roots. I know then that x minus 3 is equal to plus or minus the square root of 7. Adding 3 on both sides, I find x to be 3 plus or minus the square root of 7. Now, this method of solving quadratics can be applied sort of generally. That is, what we can do is take a general form of the quadratic equation. That's ax squared plus bx plus c equals 0. And we can use the method of completing the square to solve this for x. And it gives us a formula for solving all quadratic equations. That formula is cleverly called the quadratic formula. Here's how it's derived. To derive the quadratic formula, we begin with the general form of the quadratic equation. Now we're going to apply the method of completing the square. Our first thought is perhaps to change out our constant term. That is, let's get rid of the constant term on the left side of our equation. We'll subtract c on both sides. Now the method of completing the square only works when the leading coefficient is 1. So to clear that leading coefficient of a, we'll divide throughout by a. Now we get the cancellation as expected in our first term, so we'll bring down the x squared. Now bx over a we'll write as b over a times x to show the distinct coefficient of the x. And the negative c over a we'll think of as negative c over a. Now we're ready to complete the square. Now remember what our prescription was. It was to take the coefficient of that middle term, the coefficient of x, and take half of it, and then square the result. So here we have b over a times 1/2, quantity squared. Now b over a times 1/2
is b over 2a, and b over 2a all squared is b squared over 4a squared. Now that's the amount we'll add to both sides of our equation. Now we're ready to factor on the left. Now remember what that amount was that we squared. We squared b over 2a, so the factoring is particularly easy on the left side. On the right, we want to do a collection of our two fractions. Our first thought, though, is perhaps to put the fractions in another order, just listing the positive fraction first, or the one with a plus sign before it before the other one. And now we're ready to find a common denominator. Now notice the common denominator is 4a squared, so we'll multiply in the second fraction by 4a over 4a. This will give us 4ac over 4a squared. Now we can bring the two fractions together. So we have b squared minus 4ac over 4a squared. Now notice that we can apply extracting square roots to our problem to write x plus b over 2a on the left side, and that'll be equal to the plus or minus the square root of that right side fraction. Now we know we can think of the square root of the numerator separate from the square root of the denominator, so we think of the problem like this. And in the denominator, the plus or minus square root of 4a squared will give us plus or minus 2, the absolute value of a. You see, the square root of the 4 gives 2. The square root of a squared gives absolute a. But plus or minus 2, the absolute value of a, is the same thing as 2a. Well, now we'd like to clear that b over 2a from the left side, so we'll subtract b over 2a from both sides. Now notice that we have a common denominator. Bringing the fractions together, we get our quadratic formula.
To use the quadratic formula, it's important to write the quadratic equation in general form so that we can easily identify the values for a, b, and c. In this problem, the equation is already in general form, so we can identify a as 1, b as 2, and c as negative 3. And then we want to follow a certain prescription for using the formula. We want to, in the next step, write the formula down. Don't try to replace within it as you write it down, just write down the formula. In the next step, just replace letters with numbers. Just replace within the formula, again, making no calculations here. Perform no operations, just replace letters with numbers. And in the next step, we start to perform operations. Well, let's see. Let's talk about the replacement for just a minute. We have minus b. Now b is 2, so we have minus 2. And then the b squared means 2 squared. And the minus 4. And then a is 1. And then c, negative 3. The a value, again, is 1, so we have 2 times 1 in the denominator. Now we perform the operations indicated. 2 squared is 4. Minus 4 times minus 3 is 12. So 12 and 4 gives 16 under the radical. And fortunately, we have the square root of a square, so we can take the square root of 16 giving 4. And now we can calculate our two solutions rather easily using the plus and minus separately here. Minus 2 plus 4 would be 2 in the numerator. 2 over 2 is 1. And then minus 2 minus 4 would be negative 6 in the numerator. Over 2 would give negative 3. Now, notice that we have the square root of a square here. In this next problem, we're not going to have that situation. That is, we're not going to be so lucky as to be taking the square root of a square. Let's see what happens. First of all, we see that the equation is not in general form, so we would subtract 9 on both sides to put it into this condition. Now we can identify the a, b, and c. We write down the formula. In the next step, we replace within it. Now the a value is 1, b is 3, c is negative 9. So minus b means minus the 3 up here, and then b squared means 3 squared from here. And then minus 4 times 1 for the leading coefficient, and times negative 9 for the constant. And then 2 times 1 in the denominator. Now notice what happens under the radical. We have 3 squared 9, and then minus 4 times minus 9 is 36. 36 and 9, 45 under the radical. But 45 contains a square. It's 9 times 5. We can take the square root of the 9, giving a 3 factor in the term, but outside of the radical. And then 5 is left under the radical, so we have this. Now, this expression represents our two answers in the problem. And I've separated them here for emphasis, but often they're written like this. The two separate answers differ using a separate sign for each one of them. Okay, now an important consideration here is that we had a situation where we had a square root of a non-square, square root of a non-square, and that gave us a couple of answers that turned out to be irrational. It turns out that with quadratic equations and using the quadratic formula, we can identify the kind of answer that is going to emerge even before we start the calculation, because we can identify the number under the radical. That number under the radical is b squared minus 4ac. And it's for that reason that this value, this b squared minus 4ac, is called the discriminant for the quadratic formula. It discriminates among the different kinds of answers that can occur. Now let's talk about the possibilities here. One possibility that didn't show up in these two problems is that the discriminant turns out to be 0. If this value turns out to be 0, then this whole term goes out and we would have minus b over 2a. Now b and a are both integers because in our quadratic equation the coefficients and the constant are all integers. So we would have integers involved here, and this then would be a fraction. So we were talking about a rational number. One single rational number for the solution to our equation. All right, now, if the discriminant is positive, then it could be either a square or a non-square. If it's a square, then we have the situation that we had before. We can take the square root of a square. So we would have two answers that are both rational. If the discriminant is positive but not a square, as is the case in this problem, then we have two answers and they are irrational. Now, if we have one more case to cover. If the discriminant turns out to be negative, then we can't take the square root of a negative number in the real number system, so our solution turns out to be not a real number. So we have no real number solution to the equation. All right, one thing about solving equations generally is that we can check them. Let's go through the check. Even though it's a little bit complicated here, a little messy algebraically, let's check this for one of our answers. Now I've chosen, I think I've chosen, this one right here. And to check, you know that we would start with the original equation and plug in the value of x that we have found. So to check it, here's the original equation. I'm replacing x in both of these spots with minus 3 plus 3 root 5 all over 2. So this value is squared, and then plus 3 times that value is equal to 9. Now again, I say that the algebra is a little thick here, but it's not a real big deal if we just kind of keep track of things and write large and spread things out and stay organized. It's not a big deal. All right, squaring this binomial numerator, when we square a binomial, remember it's the first term squared, then double the product of these two. Now the product of those two would be minus 9 root 5. Double that, we get minus 18 root 5. And the last term is the square of this. Well, when we square this, when we square the 3, we get a 9 factor. When we square the square root of 5, we get 5. So this is 9 times 5. It'll become 45 in the next step. Now squaring this fraction, we know that we square both numerator and denominator, and we can think of those as separate operations. So squaring the 2, we get 4. Now sliding over a little bit, we have 3 times all of this, means 3 over 1 times this fraction, which means 3 times the numerator. 3 times negative 3, negative 9. 3 times 3 root 5 is 9 root 5. Now we have a situation where we have an equation with fractions in it, and there are a number of approaches that can be used here. I've chosen to clear the fractions. A purist would say, no, we can't clear those fractions right now. What we're supposed to do in checking an equation is work on one side of the equation or the other, and that's it. That we can't check this, and so we would have to actually write separate fractions over here and collect the like fractions and so on. And by the way, it comes out rather nice like that. It doesn't get any messier particularly. It just takes up a little more space vertically. I've chosen not to do that. I've chosen another, perhaps more speedy way to find out if I have a correct solution. And that way is to clear the fractions by identifying a common denominator, which is 4. So I'm multiplying here by 4, which means that the 4's would cancel, leaving this numerator. Now notice I've multiplied the 9 times 5 to get 45. Over here, when I multiply by 4, I get a 2 cancellation with the 4, leaving a 2 times both of these two terms. So 2 times negative 9, negative 18, 2 times 9 root 5, 18 root 5, and 4 times the 9 on the right gives 36. Now I want to collect the like terms on the left. The minus 18 root 5 plus 18 root 5 go out. That was kind of expected. We would expect that all of the irrational terms would take one another out. Then 9 and 45 and negative 18 collect to be 36. 36 equals 36, so we do indeed have a correct solution. Let me show you how to use the calculator to check this result. Now, we want to assign a value to x. You see, on the calculator, it's pretty easy for us to enter x squared plus 3x. Now, that's the left side of that equation. But to get its value, we need to assign a value for x. So we're going to assign the value that we found for x in the equation. Now, I'm going to clear this. And to assign that value, we do this. We want to store the value of x. And we do that by doing this. Let's enter the minus 3. Now I'm opening a parenthesis here to contain all the items in the numerator of that fractional answer. It was negative 3 plus or minus. Now I'll use the plus side here. Plus 3, the square root of 5. Now square root is second square root, and then 5. I'll close parenthesis, and I'll close another parenthesis. Now, this parenthesis is closing that one, and this one is closing that one. All right, that's the idea. Okay, then divided by 2, and now that's the value we want to assign to x. And I'll press the button marked STO, store. That means store as, and it's above the on button. So we're storing this as x, and then enter. All right. Now, and this is its value given in the calculator. Now let's enter the expression on the left side of the equation, the x squared plus 3x, and find out its value. Once I press enter, it will evaluate this for the value of x that we've assigned, and we hope it's 9 because we have 9 on the other side of the equation. Ah, yes, it is 9, so we have a valid solution. As you might imagine, many word problems lead to a quadratic equation for a solution. Here's one such problem. It involves a position equation which has to do with height and the effect of gravity on an object. The S here refers to height and the t time. Now the height is in feet and time is in seconds. So let's see, we have the height of an object is equal to negative 16 t squared plus v naught t. V naught is initial velocity, and that refers to the idea that the object that we're talking about may be traveling up or down at a particular rate of speed to begin with, and that's what v naught is all about. S naught is initial position. That's the initial vertical height. All right, so we can make calculations like this. How much time is required for an object dropped from 240 feet to reach the ground? Now this is actually a part of a problem that is posed in your textbook. Your textbook makes it a little more intriguing. Your textbook says, suppose someone working at a height of 240 feet drops a wrench, and they yell down below. Immediately they drop the wrench and say, "Look out below!" And so the sound, you see that they're making, travels to the ground, and so is the wrench. And the question posed is, would someone down on the ground have time to get out of the way? And it's determined that the sound goes very, very fast and therefore takes less than 1 second to reach the ground. Now what about the wrench? Well, we can find out how long it takes for the wrench to reach the ground by using our position equation. Now remember, S is the height, and t is time, and v naught is initial velocity. But if we're dropping something, then the initial velocity is 0. We're just starting with nothing for an initial velocity, and the gravity is causing that velocity to take place or to begin to take place after that moment. And the initial height is 240. All right, now the height here, the S, is the height at the end of the problem. Now we're talking about time it takes for this object to reach the ground, But what is the height when something reaches the ground? Well, the height is 0. So we replace s with 0, and then we're looking for t, so we bring down the t squared. We're looking for the t, we bring down this t, but initial velocity is 0, and the initial height is 240. So now we have to solve this equation. Now, there are a lot of ways to solve the equation. We've learned about 4 different ways to solve quadratic equations at this point. We could pop it into the quadratic formula if we want to. But because we're missing a first degree term, this lends itself well to solving by extracting square roots. So here's what I'll do. I'm adding this term on both sides to give this. I divide on both sides by 16 to find t squared to be 15. So if t squared is 15, then t is plus or minus the square root of 15, but only the positive value makes sense when we're talking about time. Time has no negativity associated with it in terms of what we're talking about here. And so the time then is approximately 3.87, and that's seconds. So it'll take the wrench 3.87 seconds to reach the ground, and look out below took about, well, a little less than a second, and so a person down below has about 3 seconds to get out of the way. Plenty of time to be safe.
A model rocket is projected upward from ground level according to the height equation h is equal to -16t squared plus 192t, where h is the height in feet and t is the time in seconds. After how many seconds will the height be 432 feet? Well, here, of course, we're given a height, and so we'll replace h in our equation with 432. Now, to begin the solution, we'll subtract 432 on both sides to have all terms on one side of our quadratic equation. Now, of course, our prescription is to factor. We see a common factor of 16, and actually we'll take out that entire leading coefficient of -16. When we factor the -16, we get t squared minus 12t plus 27. Now factoring the trinomial in parenthesis, we get t minus 3 times t minus 9. The values of t that cause each factor to become 0 are 3 and 9. Now you may be wondering how it's possible for 2 different times to give a height of 432 feet. Well, here's how. You see, as the rocket flies, it goes through that 432-foot level on the way up, and then it comes back down and goes through that 432-foot level again. So we say then that the rocket will be at a height of 432 feet after 3 seconds going up, and again after 9 seconds coming down. Consider another part to this problem. When will the rocket hit the ground? Well, we go back to our basic equation, and we let h be 0. And we can do that because the height is 0 when the rocket is on the ground. Now, to solve our equation, we can solve by factoring, but another technique we can use here is to divide throughout by -16. Now, when we do that, the equation looks like this. Well, now we can take out the common factor t and find the values of t that cause